You know, some of the most chaotic things you can imagine, think stock market trades or even radioactive decay, they aren't nearly as random as they look. It turns out they've got this hidden pulse, a kind of secret rhythm. And in this explainer, we're going to uncover the beautiful, surprisingly simple math that governs pure chance, giving us the power to predict the unpredictable. So that's the big question, right? Can we really find a predictable pattern, some kind of order, in events that seem completely and utterly random? Well, the answer is a huge yes, and it's a concept that helps us model the world in some pretty incredible ways. Just think about calls flooding into a busy help desk. You have no idea when the next call is going to come in, right? There's no schedule. From our point of view, it's just random. Or what about the clicks of a Geiger counter? I mean, the decay of one atom has absolutely zero influence on when the next one decides to go. Each one of those clicks is a truly independent, random event. Heck, even something as ordinary as cars passing a specific spot on a highway follows this exact same pattern. All these things seem so different, but believe it or not, they're all connected. So how in the world do we make sense of all this chaos? Well, the secret is that this type of randomness, which seems so wild, actually plays by a surprisingly simple set of rules. And once you know them, you can start to tame it. Let's break down how it works. It really just boils down to two core ideas. First, the events are totally independent. One phone call coming in doesn't make the next one more or less likely to happen. And second, while any single event is random, the average rate of these events, we call it lambda, is constant over a long period of time. You could almost think of it like a perfectly random drummer who still keeps a steady average beat. And this brilliant idea, it has a name, the Poisson process. It's this incredibly powerful model for counting these random independent events that are happening at a constant average rate. This simple definition right here is the key that unlocks, well, everything else we're about to explore. All right, now let's see how these simple rules lead to one of the most fascinating and frankly counterintuitive results in all of probability. It's a little puzzle I like to call the paradox of waiting. So imagine you're just watching these events happen. They pop up at completely unpredictable times. One moment there's a 5-minute gap, the next it's only 1 minute. It's all over the place. Okay, so let's make this personal. You're at a bus stop. And these buses, they arrive according to a Poisson process. You've already been waiting for 10 long minutes. Your intuition, your gut, is screaming that a bus must be just around the corner, right? It's gotta be. Nope, not at all. In the wild world of the Poisson process, those 10 minutes you've already waited, they mean absolutely nothing for when the next bus will arrive. It's like you just showed up that very second. The reason for this totally bizarre outcome is a core feature called the memoryless property. The process literally has no memory of what just happened. The clock just resets itself at every single moment. So your expected wait time from the second you arrive is the exact same as your expected wait time after you've already been waiting 10 or even 30 minutes. It's crazy, but it's true. But this memoryless thing is just the beginning. Poisson processes also have these elegant little superpowers. They behave in these really clean, predictable ways when you start combining them or splitting them apart. And this flexibility is what makes it so powerful. If you merge two independent streams, like, say, calls for product A and calls for product B, they just combine perfectly into a brand new single Poisson stream. And the new rate? It's just the sum of the two original rates. And what's really cool is that it works in reverse. If you randomly split one stream, like a line of customers being sent to two different cashiers, each new line becomes its own, slower Poisson process. The beautiful underlying structure always stays intact. Okay, so this is all really neat, but why does any of this matter? Well, it matters because this entire framework lets us solve some famously tricky probability puzzles with, honestly, surprising ease. Let's start with a classic one, the coupon collector's problem. If there are, say, n different coupons hidden in cereal boxes, how many boxes do you think you'd have to buy, on average, to collect every single one? Using our new tool, we can model this perfectly. We just have to think about the discovery of each of the n coupons as its own separate, independent Poisson process. So the problem just becomes, how long do we have to wait for every single one of those processes to have at least one event or arrival? And when you do the math, when you calculate the expected waiting time for each new coupon and add them all up, you get this beautifully simple approximation. The average number of boxes is about n times the natural log of n plus a constant. So for 20 unique coupons, you'd expect to buy around 72 boxes. See? Our abstract model gives us a concrete, powerful answer. Okay, let's try an even more famous puzzle, the birthday problem. How many people do you need to get into a room to have a better than 50% chance that at least 2 of them share a birthday? The answer always blows people's minds. And again, we can frame this using our model. Just imagine 365 separate Poisson processes, one for each day of the year. Every person who walks into the room is an arrival in one of those processes. So what's a shared birthday? It's just the second arrival in any one of those 365 streams. And when you analyze the probability of that first collision, that second arrival in any one of those streams, the Poisson approximation tells us that the number of people you need is about 24.6. Now get this. The exact answer, calculated the traditional, much harder way, is 23 people. 23. The fact that our Poisson model gets us so incredibly close is, well, it's just astounding. It really shows you how powerful and versatile this way of thinking about randomness really is. And that, really, is the key takeaway here. The Poisson process isn't just some abstract math formula. It's a lens. It's a way of looking at the world that helps us find a predictable, powerful rhythm that's hidden inside the noise of what looks like pure, untamable chance. So I'll leave you with this question. Now that you have this tool, what other random events in your own world can you start to see in a new light? From website hits to shooting stars, the rhythm of randomness is everywhere you look, just waiting to be seen.